Oh, hi. Welcome to Math 232 at SFU. What we're doing in this little add-on lecture is it's not a specific, it's actually, in fact, not a lecture. What I'm doing is going to just provide a little bit more detail and some examples for section 4.6. So we have the idea from earlier of representing a vector, the coordinates of a vector in a basis other than the standard basis in any basis that we wish. And now we are enlarging that idea to represent a linear transformation in a basis not the standard basis. And so I'm just going to actually work through several of the questions in the textbook, just for you to follow along with. I suggest maybe trying the questions yourself first, and then seeing if you make headway or not, and then you could fast forward through that question if you understand how to do that one, or it allows you to stop and say, okay, what was it that I didn't understand in order to do this question. Okay, so this is rather a random selection of examples. The first one I'm going to do is question question B1. So that is, we're talking about section 4.6. So that is on page 294. So what we have is a basis for R2. The basis looks like this, V1 and V2. And that's a basis for R2. We have a linear transformation which maps R2 to R2. So we have a domain of R2 and we have a codomain of R2. And then our linear mapping is written out like this. So this is telling us what happens under the linear transformation to the first basis vector. And then we have what happens under the linear transformation to the second basis vector. Okay, and then what we're supposed to do is the question asks us to determine the matrix of the linear transformation in the basis B, and use that. Now that's part one, and then use that to compute this guy here, the linear transformation of minus V1 plus 3V2. That, and we want that in the basis B. Okay, so the first thing I'm going to just say about this is let's think about what we've been doing before we introduce this idea of a different basis. That is back when we just had the standard basis. So what we were doing is we were saying that the matrix of a linear transformation, we didn't subscript it at all, but now I'm going to subscript it. Let us just let S. So I'm going to say here S is a standard basis. This is what we've been doing. The matrix representing the linear transformation in the standard basis, the way that we've been able to do that is we have been able to form the matrix whose columns are the linear transformation of the first basis vector relative to the standard basis, and we went the whole way across, and we would then have, so we went through each basis vector. And these guys, E1 to En, are the standard basis vectors. We did that. And then we were able to calculate the linear transformation of some vector x, where x is a linear combination of the standard basis vectors. So in this case here, x is going to be equal to C1 E1 plus C2 E2, etc., the whole Cn En. So we're saying what happens under the linear transformation to this vector x, and because we have these basis vectors, x must be a linear combination of the basis vectors. And what we saw was we were able to calculate this by taking the linear transformation matrix and multiplying it by the vector. We're going to do exactly the same thing here, but instead of, in fact, let me get the S in here. Instead of this guy being relative, all of these guys being relative to the standard basis vectors, they're going to be relative to the basis vectors in the named basis. Okay, so let's, with that in mind, head into the answer for question B1. Okay, we are being told here what happens to the basis vectors. Okay, so let's just, again, thinking this way. I know these are not the basis vectors, but I'm thinking it's telling you if you have a basis vector, what happens to it? Pretend the basis vector is this. I mean, this is a sort of pretend move. What if V1 was this? I mean, we don't even know what they are, right? But what if it was a standard basis vectors? What are we telling us? It's telling us that the linear transformation of V1, of the first basis vector, would be 2 times the first basis vector plus the second basis vector. That's what it's telling us. And in this case, that would be 2, 1. Okay, and if V2 was the second standard basis, what we're being told, I know that it's not, V1 and V2 are not these two guys, but they could be. And if they were, we would be thinking like, we would perhaps already be able to think of it like this. It's telling us we're doing 3 times the first basis vector plus 4 times the second basis vector, and we get this guy here, 3, 4. Okay, so when we're thinking about this, then actually, with this sort of thought in mind, because we're being told what happens to the basis vectors, the matrix of the linear transformation relative to the basis B, of whom the basis vectors are V1 and V2, has to be these exact two things, 2, 1, and 3, 4. Whatever these guys are, they belong here, here, and here, but it does not change this relationship, 2 of the first one and 1 of the second one. So we can immediately write this out because we're told what happens to the basis vectors. We can then use that to calculate the linear transformation of some other combination of the basis vectors. That is this guy here. That's going to be our matrix representing the linear transformation multiplied by a vector. I think that was the vector given to us. Use that to compute. Oh, I see. Yeah, so multiplied by the vector that represents the linear combination of these basis vectors. So this minus 1, 3 is coming from the fact that I am asking what happens to this linear combination of the basis vectors. I can now do this multiplication. 2, 1, 3, 4. I multiply by minus 1, 3, and I get 7, 11. And that answers the 2 questions. Okay, that is question B1. Okay, next one I'm going to do is question A3. Let me just get the thing out. A3. A3 says assume L is a linear map, and we want, so we're going to say L is a linear mapping. This is the question. And we want to compute, we are going to compute the matrix representing L relative to the basis B. And this is what we are told. The linear map looks like this. The vector 1, 1 maps to minus 3, minus 3, and the vector minus 1, 2 maps to minus 4, 8. And of course, we need to know what is B, and that's given to us. B is this basis here, 1, 1, and minus 1, 2. So first thing I'm gonna do is look and say, okay, hang on, what am I being told? I've got a basis for R2. It's got 2 linearly independent vectors in it, and I'm being told, hey, look, this is the linear transformation of the first basis vector, and this is what happens to the first basis vector under the linear transformation, and this is what happens to the second basis vector under the linear transformation. Okay, however, these things here, right here, those things right there are relative to the standard basis. Okay, so what I now need to do is figure out, okay, well, what I wanted to do here is I need to compute L of B, and the columns in there is right here. It is this. What happens? The first column is what happens to 1, 1, but it's not just what happens to 1, 1. It's with respect to the basis we want to this basis right here. And then this is what happens to -1, 2. That's what we're looking at. And that's also, again, with respect to B. Okay, so that is our with respect to the basis B. Okay, so I now take, I know what happens to this vector. It results in this vector under the linear transformation. I know for both of them what that is. What I then need to do is take this guy and figure out what the components of that guy are in the basis B. So that question is this: -3 minus 3, that is equal to, and I'm going to write this down. Like you may not just be able to figure this out of your head, but I'm just going to show you this is true, so I can show you what the matrix is, and then I can show you how to get that -3 and 0. But let's just write those down so we can get a sense of what's happening here. Okay, so we can check that these are correct. -3, like you can just read across here, -3 is -3, and then -3 is well, -3 again, and then here -4, I have -4, and then 8, I have 8. Okay, so I can see that what these vectors are in S, those vectors in S, I observe this, what combination they are of the basis vectors of B, and then that tells me that this -3 -3 relative to the standard basis is in fact -3 0, the coordinates in basis B. Okay, and then here this one is the same thing. -4 8 S is 0 4 in B. Okay, how would I see that if I couldn't just write that down? What I would do is, okay, what am I doing? I'm changing coordinates from S to B. So I would then put the basis vectors of B here, and I would put the basis vectors of S here. And I would row reduce until I got I here, and then I would have what I wanted here. Now you'll notice I'm starting here. When I am changing from S to B, this thing here is the identity matrix. So this operation actually is going to provide, at the end of the day, the inverse of this matrix. That's an important point to see. So this, in fact, is equal to 1 minus 1, 1, 2 to the -1. You can go through and do it by Gaussian elimination, but it is also the inverse. You can see that because this is exactly the same procedure we use for finding an inverse. Okay, so what did I get when I did this? I got this, the inverse of this matrix, to be equal to 2/3, 1/3, minus 1/3, 1/3. Now, if I take P, S to B, and I multiply that by -3 minus 3, like that, that will look like this. 2/3, 1/3, minus 1/3, 1/3, and I will multiply by -3 minus 3, and that, in fact, is -3 0. Okay, that's how I get these. That is how I'm getting these coordinates here, that guy and that guy. And do the same thing with this one here, and then you'll find that you get these coordinates here. Okay, so that is now, I now can write out what that matrix I wanted to find is, that I was trying to compute. The linear transformation with respect to B is what happens to the first basis vector under the transformation written with the coordinates of the basis B. There it is. That's question A3. Okay, let's do another question. Just keeping going here. B2. We'll do B2. We're page 294. B2. Okay, let's take a look at this. We have a basis, which consists of 3 vectors, v1, v2, and v3. There it is. Okay, and we've got a linear map from R3 to R3. And we want to determine this. We want to determine the linear transformation of some vector x relative to b, where let's see what we're given. We're supposed to determine this. Let me just write that. Determine this for the given x. So let's just get these things out that we're given. We're being given a vector with coordinates in the basis b. Okay, so let's see what we have here. We were getting told that the linear transformation affects the first vector in this way, 2v1 plus v2 plus 2v3, and that the linear transformation affects the second vector, basis vector, in this way, 2v2 plus v3, and that the linear transformation affects the third vector in this way, 4v1. Sorry, that's a bit messy. Let's fix that. 4v1 plus 3v3. And we're told we have a vector coordinates given to us from relative to the basis b, looking like that. And we want to determine this guy here. Okay. All right. So let us just write out what that is. This guy here that we're going to try to determine, that is, what is the linear transformation applied to x? That is the matrix representing the linear transformation relative to the same basis here, multiplied by the x in the coordinates. Okay, these all have to match. They have to be in the same basis. Okay, so let's just notice what we're given. We're given that. And of course, if we can find this, then we'll get that. That's the objective, the method I'm going to use. Okay, so let's think about this. We want to understand, well, we can easily understand what is happening to the basis vectors. That is, let me just sorry, I have to. Okay, sorry about that. What we're going to do is we are being told right here what happens to the basis vectors. This is not always the case. Our next example, that won't be the case. We'll see how that's different. So what we can then write is, okay, we can write the matrix of the linear transformation relative to B, because we're being told what happens to those basis vectors. And that is what happens to this first basis vector v1. It is 2 times v1 plus 1 times v2 plus 2 times v3. What happens to the second one? It is 0 times v1, 2 times v2, and 1 times v3. And then what happens to the third one? It is 4 times v1, no times, there's no v2, and then 3 times v3. So we can write that down. Okay, we could be thinking of v1 as a standard basis, just to sort of make sure we get our mind around what's happening. What if I'm thinking, what if v1 was this? I mean, it's not necessarily that, but it isn't one of the options. V1 could be that. What would that mean? We would be looking at 2 times v1. If v1 was that, we would be thinking in this first statement here, this guy here, that first statement, we'd be thinking, okay, hang on, v1 is this, and what's going to happen to v1 it is going to be 2 times 1, 0, 0 plus 0, 1, 0 plus 2 times 0, 0, 1. Okay, that's this. 2 times V1 plus V2 plus 2 times V3. That would be if V1, V2, and V3 were the standard basis vectors. They are not. There are some unspecified ones, but we are told what is happening to the basis vectors. And you see that I get here 2, 1, 2. And that is indeed this column. Okay, that's because no matter which things I put here, we're always getting this combination 2, 1, 2 of whatever the vectors may be. Okay, so now that allows me to calculate L x b, which is equal to L b x b. That is this guy 2, 0, 4, 1, 2, 0, 2, 1, 3, and then that is multiplied by. Now I'm checking. I'm given this vector relative to b, so I can simply put that here. If I was given this vector relative to s, I would have to convert it, the coordinates, to the new basis, but I don't have to do that in this case because I'm given it that way. Okay, so then I get this guy here. I do that multiplication. Okay, that is question B2. Let's move to another one which is, I think, a more typical type question in that we're not given what the linear transformation does to the basis vectors. We're given what the linear transformation does to a single vector. Okay, so let us see the difference here. Okay, this is question B11. We are told let's see, I'm looking for what the basis is. 1101. Oh, there it is. Okay, so here I'm just getting the question down properly. We're told here's a linear transformation, and it behaves in the following manner. It operates on a vector from R3, and it does this. I'll try not to make any small arithmetic mistakes because that can be highly confusing. I think I've got the transformation copied down correctly. Okay, so that is our transformation. And we are given that we want to, our goal is going to be to compute L, the linear, to provide the matrix of the linear transformation relative to with respect to the basis B, which we have, need to know what that is, and it is this guy here. So here are the basis vectors. 3 vectors, linearly independent, forming a basis for R3. Okay, and we are given a vector in R3 looking like this. The first thing we're noting is we're paying close attention of which things are relative to what. So we're seeing this guy like this. With no subscript, we're like, this is being given relative to S. So that means really what we're being told here is this guy is 1 of this minus 2 of that plus 3 of that. That's what that's telling us. Okay, these coordinates are relative to the standard basis vectors. Okay, what we want to do is calculate the linear transformation. We want to calculate the linear transformation, the matrix of the linear transformation relative to these vectors. Okay, so the first thing we can do is calculate, the first thing we will do is calculate what the linear transformation does to each one of these vectors. So I'm using this right here. I'm going to say, what is the linear transformation of 1, 0, 1? That's this first basis vector. That turns out to be -1, 0, -1. Now let's recognize that this is that vector the coordinates here are relative to the standard bases. All I've done is take a linear transformation, here it is, and say, what happens to 1, 0, 1? And then I'm going to say, what happens to 0, 1, 1? Okay, now I get here minus 10, minus 4, minus 3. And then what happens to 1, 1, 1? That is minus 8, minus 2, minus 3. Okay, let's realize that what we could, of course, have done here too is we could have provided L the relative to S, just like we have done before. Okay, that is quite straightforward. We're looking here at 2, 1 minus 2, 1. Sorry, let me try that again. 2, 1, 0. 2, 1, 0. We're looking at minus 7, minus 2, and minus 2. Minus 7, minus 2, minus 2, and then the minus 3, minus 1, minus 1. Okay, that is, I can write that down directly like that, or I could go ahead and do it this way. What happens to the first basis vector? That's 2, 1, 0. What happens to the second basis vector? That is minus 7, minus 2, minus 2. What happens to the third basis vector? I'm writing this with respect to the standard bases, okay? And that's what happens, okay? Now, minus 1, 1, okay. Now what I'm saying is that when we do this, when I'm hopefully not confusing the issue here, but when I just take the linear transformation and represent it relative to the standard basis vectors, I do exactly what I'm going to do over here. I calculate the linear transformation for each one of the basis vectors, and I put them in the matrix. And the reason why I don't have to do anything else is because these vectors are relative to S. When I do it over here, I do exactly the same thing. This part here is all to do with the basis B. I calculate what does the linear transformation do to each one of the basis vectors. When I do this computation, I get a vector whose coordinates are relative to S. Because I am trying to give the linear transformation relative to the basis B, I need to take each one of these guys and change it from the standard basis to the basis B. One way I'm going to do that is one way to do that is to say I'm going to compute the matrix that is going to change a vector from the standard basis to the new basis B. And I do that by taking the basis vectors of B, augmenting that with the basis vectors from S, and row reducing until I have I, and I have what I want here. And this is exactly how we find an inverse. So actually what I'm looking for is that this matrix here will be the inverse of this. And I have computed that. Let me see if I can write that down. I have computed that already. You need to know how to be able to convert and compute an inverse of a 3x3 matrix. Okay, you do that by row reducing. Okay, there. I got that there. Now, what I want to do is convert each one of these vectors here. Each one of those vectors needs to be, I need to find the coordinates of each one of those vectors relative to B. And I simply do that by taking P, S to B and multiplying by each one of those vectors. That would be like minus 1, 0, minus 1 is the first one. Let's just do that calculation. I would go here and I would go 0, minus 1, 1, minus 1, 0, 1, 1, 1, minus 1. And then I multiply by minus 1, 0, 1, and I get minus 1, 0, 0. So this right here, This is relative to B, and this is what happens to the first basis vector under the linear transformation with the coordinates represented with the coordinates from the basis B. That is the first column of the matrix that we are looking for. We are looking for this matrix, and that now is our first column. 0. Okay, that is here. What happened to the basis vector? Take what happened to the basis vector and do a change of coordinates. That is that column. Okay, and exactly the same thing for the other two. I suggest you stop the video and do it yourself. But what I'm going to do, I'm just going to write out the answer. I'm going to take this guy here, that vector. What's going to be this vector here? What happened to the second basis vector? It was transformed to this. Now I'm going to take that and represent it in the coordinates from B. Okay, and then I do the same thing for the third one. The third one is here. Okay, I'm going to take this guy. I'm going to do that. So what I'm saying for you to do is you're going to do this exact operation right here with the other two vectors, and you should get this thing. So now I have this matrix here. Hang on. Sorry, I got this. Sorry, these numbers came from, these are not the right numbers. I copied them down from somewhere around. The numbers are actually this. Sorry about that. Okay. You should check what I've done. Okay, so that is what we were asked. What we were asked to do? Let's see what B11 says. Yep, and now what we want to do, okay, so we got told to determine this. So we found this, that's part one. And then we're asked, use this to find what happens to X and represent what happens to X, some vector X, in with coordinates, with the vector coordinates being a relative to B. That's what we're being asked. Okay, so how do we do that? Well, we are told what X is. X is, let's scroll back up here, it's right here. 1 minus 2, 3. But let's remember that is relative to the standard basis vectors. So what we need to do is transform X. We have to represent it. We have to do a change of coordinates. So we're going to go ahead and do that. We have that same matrix to do that with. That is 0, minus 1, 1, minus 1, 0, 1, 1, 1, minus 1. I'm gonna then multiply that by 1 minus 2, 3. And what do I get when I do that? 5, 2, 4. 5, 2, minus 4. Let's see, 1 minus 2, minus 3. Yep, minus 4. Okay, that isn't gonna now allow me to calculate what is L X of B being L of B times by multiplied by X of B. So now I can take that product. I get L of B, that is this minus 1, 0, minus 1, 0, 7, 5, 0, minus 10, minus 7. I'm going to multiply that by 5, 2, 4, minus 4. And I'm going to get some number. I got here minus 1, 6, 8. That vector is coordinates relative to B. Okay, let's observe something here. I could change this back relative to the, this is not part of the problem, but I could change this back relative to standard basis. So I could go like this, 8, that is equal to, what does this mean? -1 multiplied by the first basis vector, 1, 0, 1, plus 6 times the second basis vector, plus 8 times the third basis vector. Looks like that. And I get this, 7, 2, 1. That's relative to the standard basis vectors. Okay, we have already said what this guy is, L relative to S. That was this thing here. 2, 1, 0, -7, -2, -2, and -3, -1, -1. Now, let me take this, make this calculation. LS times XS. 2, -7, -3, 1, -2, -1, 0, -2, -1. And I'm going to multiply by the original vector S. That gets me this, 1, -2, 3. So now I'm doing the same linear transformation, but I'm doing everything relative to the standard basis vectors. I get this right here. Holy cow, right? Holy cow, look at that. That's what has to happen. So the point is here, I can do the linear transformation. I can do the linear transformation, everything relative to the basis vectors in B, and I get the answer in B. I can convert that to S. I can do the same calculation. Here, this is L of X S. I can do the same calculation relative to the standard basis vectors, and I get the answer relative to the standard vectors. I could also, of course, convert this to this using from S, P from S to B. I could go that way. Okay. You can do the whole calculation. We can do all the calculations with respect to the standard basis vectors, and then you can do the same calculations exactly relative to a different basis. Okay, I'm going to keep going here. I'm going to do a couple of more questions. I'm going to take a look at question B12. Here's question B12. Determine a geometrically natural basis. Geometrically natural basis, that's what we're being asked for. And then determine the B matrix of the transformation. So B12, what we're trying to do is find a matrix that does this transformation. So let's just draw a picture of what this looks like. What is happening here? We have a line. That line is T3, 2. Okay, and we are considering any other vector in the plane, and then what we are doing is we are doing an orthogonal projection down, and then what we're asking for is finding this. Okay, so we're saying take any vector in the plane, project it onto that line, and then tell us what the perpendicular component is. Set up a matrix to do this, and not only that, set up that matrix in what would be a natural basis. Okay, so what does this mean? Well, think about what is an obvious basis to pick. It makes sense to have one of your basis vectors right along here, because that's the line that you're projecting onto. So I'm trying to pick a geometrically natural basis. I'm like, well, I'm projecting onto this line. Why don't I put one of my basis vectors right along that line? So that is going to be then, I'm choosing my basis. So my first basis vector is going to be 3, 2. I need a basis for R2. I need 2 vectors. Now, what would be the most obvious second basis vector to pick? I think the most obvious thing to pick, particularly given that we're doing projection and that we're also looking at things that are perpendicular, my second basis vector is going to be right here. Okay, it's going to be along this line here, perpendicular to my other basis vector. And that will form a linear independent set. How do I figure out what that vector is? Well, those two, the blue line and the red line have to be, they are perpendicular the way I've chosen them. So that means that the dot product 3, 2 dot x1, x2 is 0. That means if I put this into a matrix, it means 3, 2, 0, and then I can row reduce that. I get 1, 2/3, 0. I see I have one free variable. X2 is t, and that x1 has to be minus 2/3 t. Okay, so that then tells me that x1, x2 equals t times minus 2/3 1 is orthogonal. All those vectors are orthogonal to 2, 3. I'm just going to pick t equals to 3 just so I don't have any fractions, and I'm going to put that here. That's my second basis vector. Now, what does the matrix that finds that this guy here, what does that matrix look like? Now I can simply write it out. What happens to this basis vector? Well, you just looking at the picture here, you're like, look at the red line. There is no component perpendicular to the red line. So the red line is going to go nowhere. Like, it is 0. There's no perpendicular component to the red line. And then if you look at what happens to the second basis vector, this guy here, what happens to him? Well, he is actually just the perpendicular thing that you're looking for. So the transformation selects him, and we are done. This is much easier than setting this matrix up in the standard basis, because the basis vectors are right along the lines of what we're talking about, the parallel and perpendicular components of the vector. When you think of these two components here, we're decomposing a vector into those two things, and once we put our basis vectors onto those two things, that is what we get. So that is a nice feature. I'm just going to do one more example like that. That is going to be B14. B14. So this is asking, it's the same question. It's asking for perp 2, 1. So this is now in R3. So I'm going to, following the same line of logic, I'm going to select the basis vectors, one of which is along the line that I want to find the perpendicular component to. And then I'm going to pick 2 other basis vectors, each of which are orthogonal to this. So you can do that yourself with the dot product. Okay, and then I will be able to, exactly the same way, write this out. It's going to be this. What happens to the first basis vector? There's no perpendicular component. What happens to this guy? It is perpendicular, so that it just stays there. What happens to the third guy? It is perpendicular. There. We are done. So we can easily write into the matrix, this is relative to B, what happens to each one of the basis vectors, because we can see geometrically what that is. The question B15, which was asked in the assignment, I think you can just leave that. We didn't do reflection in R3. Leave out. Okay, we're going to leave that out. How am I doing for time here? Okay, let us, should we possibly take a look at another one? I think what I'm going to do actually is I'm going to stop this here, because actually we're getting close to the class lecture time. So I'm going to stop this thing here, and then I'm going to come back and do a second part video where I do 2 more questions. So that'll be a part 2 of this adventure here. Thanks, guys.